Okay, this is John Allison with Arkansas. I am reporting the solution to number 2 on the BC exam from 2025. Y'all bear with me. Remember, I do this cold, and I'm not going to look at the problem until it is time for me to start working on it. I want to make sure that I can see where I'm going to start. Okay, so now that you can see what I'm doing, I'm going to go back to the problem. I'm going to open it. It's been a couple years since I taught BC, so bear with me if I make mistakes. Bear with me. I do this partly like this because I want to let kids know that it's okay to make mistakes, and teachers know it's okay to make mistakes. And we don't have to be perfect on this exam to score well. So we have the curve. Oh, and another thing, I don't show you the problems on here because it's a College Board copyright violation. So I have a link in the description of the video that will take you to the actual released FRQ, and you can follow along from there. So we have problem number 2 from the BC exam. I wrote this on every test video a little while ago, but this is 2025 release FRQ number 2 from the Calculus BC, AP Calculus BC. Exam. And we have a curve C that's defined by r theta equal to 2 sine squared theta for 0 less than or equal to theta less than or equal to pi. Curve C and a semicircle. R equals 1/2. I'm going to go ahead and sketch this graph on here. I would not do this on the exam if I was taking it, but so that you can see what I'm doing here, I'm going to sketch this graph. So this is r theta, and this is a semicircle for r equals 1/2, all for 0 less than or equal to theta less than or equal to pi. Make sure you can see all that. You can, okay. On the rate of change of r with respect to theta at the point on curve C where theta equals 1.3. So where theta equals 1.3, we want the rate of change of theta. So when theta equals 1.3, 2 sine squared theta, 1.3. I'm going to go ahead and find that point. I may not need to, but I'm going to go ahead and find it. So hit my calculator already. I'm in radians. So I'm going to go ahead and type in 2 sine 1.3 close parentheses squared. The calculator, that's the way the notation works. And so that R is 1.856. When I look back at my graph on here, this is at 2.0. We think about that pi over 2. We have pi over 2 here. This is 1. Sine is 1, so 1 squared, so that's going to be 2, so that's correct. All right. So that was about 1.856. 1.3 would be somewhere probably up in here. Theta would equal 1.3. So this is the point. 1.856, 1.3, where we have r and theta. And so if we want to find the rate of change in r, we need to find r prime with respect to theta, or dr d theta is going to equal, this is going to be 4 sine theta times chain rule on the sine theta is going to be cosine theta. And so that's going to be rate of change with respect to theta. That's all we have to do. Okay, so it should be pretty simple. 4 times sine 1.3 times cosine 1.3. And we could enter that in the scientific calculator, but I'm going to go ahead and enter it and get a decimal approximation here. So I will get 4 sine 1.3 times cosine 1.3. Gives me 1.031. We don't have any units on this, so we don't have to put units. Okay, so B says, that was part A. Part B says, find the area of the region that lies inside curve C, but outside the graph of the polar equation, R equals 1/2. So that's this region. We're excluding this part in here. So we need to find the total area from here to here, and then we need to find the area from here to here. So, interesting. Let's see what we can do here. We can find from this point, we can find theta. To this point, we can find theta. We need to know where does 2 sine squared theta equal 1/2. And so that means sine squared theta equals 1/4. Well, this is a nice one. So that means sine theta is going to equal plus or minus 1/2. And that's going to occur when theta equals pi over 6 and when theta equals 5 pi over 6. So we're going to integrate. This is going to be the area from the outside curve to the inside curve over that domain from pi over 6 to 5, oh, no, what, all right, 5.6. 5 pi over 6. Pi over 6 to 5 pi over 6. And this is going to be, recall this is going to be 1/2 r squared d theta. So let's see here. This is going to be the outside area, r squared d theta. And I'm going to subtract the inside from that. And pi over 6, 5 pi over 6. This is going to be 1/2 times the r here is 1/2. So that's going to be 1/2 squared d theta. That should be the correct setup. We're going to find the area. So I'm going to type that in the calculator. Oops, r squared. I need to put that in there. R squared. Do this again. Let's go ahead and set it up for the calculator. 5 pi over 6. I'm going to do 1/2. This is going to be 2 times sine squared theta. All squared d theta minus, go ahead and make this 1/8. How about that? Pi over 6. 5 pi over 6 d theta. So we'll put that in the calculator and do math. Go to integration. And I'm going to do pi over 6. Lower limit. 5 pi over 6 as the upper limit. Then inside the integrand, I'm going to go ahead and, well, let's just type it in here like this. Let's do 0.5. Open to the parentheses. And do 2 sine squared theta, or sine squared x, since we're. And then I'm going to close my set of parentheses and square all that. dx We'll subtract the integral from power 6 by power 6 of 1/8 dx. And for that, I get 2.066 or 0.67. Either way. I'll look at my graph real quick and see, does that look reasonable? This is from 1/2 to 1/2. 2, so it's going to be 1 to 2. And it goes outside of that a little bit, so that looks fairly reasonable. Looks like a reasonable answer. Just want to double check it, make sure it's reasonable. All right, part C. So it can be shown that dx d theta equals 4 sine cosine squared theta minus 2 sine cubed theta for curve C. So we're going to look at for 0 less than or equal to theta less than or equal to power 2. I'll keep around that. Find the value of theta that corresponds to the point on the curve C that is farthest from the y-axis. So from 0 to power 2, we want to find the point on the curve that's farthest from the y-axis. We want the maximum then for x, the maximum x value. And dx d theta is the change in the x value with respect to theta. And so we want to know when that equals 0. And then we'll check and see what's happening on either side of that. So, if we do this, we're going to go to, let's say, 4 sine theta cosine squared theta minus 2 sine cubed theta equal to 0. All right, I'm going to divide by 2 first. I'm going to factor out the sine. So I'm going to say divide by 2. And it's going to be sine theta times cosine squared theta minus sine squared theta equals 0. I know by my trig identities that cosine squared theta minus sine squared theta is cosine 2 theta. So when sine theta equals 0, or when cosine 2 theta equals 0, this occurs when theta equals power 4. And this occurs when theta equals 0 on the interval from 0 to power 2. So this looks like power 4 is our best option. So if theta equals power 4, this is a candidate. Of course, our endpoints are candidates, but when you look here, when theta equals 0 and theta equals power 2, it's definitely not farthest from the x-axis. So that means we need to show, we're going to say from theta equals 0 to theta equals power 4, dx d theta is greater than 0 because x, the distance from the y-axis is increasing as we go here. And then from theta equals power 4 to power 2, dx d theta, the x-coordinate is decreasing, so it's less than 0. That means that x is increasing from 0 to power 4, decreasing from power 4 to power 2. So we can say that x of theta changes from increasing to decreasing at pi over 4, theta equals pi over 4. So the maximum x value occurs when theta equals pi over 4. And now we have part D. Particle travels along curve C, so at d theta dt is equal to 15 for all times t. Find the rate at which the particle's distance from the origin changes with respect to time when the particle is at the point where theta equals 1.3. Find the rate at which the particle's distance from the origin changes with respect to time when the particle is at the point theta equals 1.3. So since r, call it r of theta, equals 2 times sine squared theta, then dr dt equals 4 sine theta times cosine theta times d theta dt. A little implicit differentiation there. And we are looking for the rate at which the particle's distance from the origin changes. That's dr dt when theta equals 1.3. We know that d theta dt is always 15. So that means that dr dt when theta equals 1.3 equals 4 times sine 1.3 cosine 1.3 times 15, or 60 times sine 1.3 times cosine 1.3. I'll go ahead and type that in the calculator. So I'm getting 15.465 would be the rate at which the distance from the origin changes with respect to time. So that should be all for question number 3 on the BC exam. Again, it's been a couple years since I taught BC, so if I messed something up there, please bear with me, forgive me. I'm going to go on to question number 5 next.